In this lecture, we'll be talking about an orbit following control law. We'll start by describing a circular path mathematically. Then we'll create a frame of reference based on that circle and define the vehicle motion in polar coordinates. We'll then develop a control law to converge to the orbit and present a feed-forward roll angle for the orbit. But before we do that, let's take a look to see what this looks like in sim. So, see, I have my aircraft plotted here, and we have just a small circular arc developed right here. And this circular arc is defined by first an origin point. So we'll call that the center point of our orbit. And right here I've placed that center at 600 in the x direction, 0 in the y direction, and negative 100 to approximately match the altitude of the aircraft. Then we'll define an orbit radius, 400. So if we look here, we have 1, 2, 3, 4, 5, 6, right where my mouse is going to be right at the center of that orbit. And then the radius we've defined as 400. So coming back 4, 1, 2, 3, 4, and there's the orbit that we have. So we define this circle, and we call it an orbit. Define the circle, we'll start, and the goal is we want to have the aircraft move towards that circle and at the same time start to follow that circle. So as we go around, as we let it go for longer and longer, you'll see that the distance between the aircraft and the circle gets smaller and smaller. So the aircraft approaches it. If we were to change the position of our circle, so now let's center it right where the aircraft is. Oops. Now we see that 1, 2, 3, 4, there's the orbit that we're trying to follow. So if we start inside of it, now we'll converge, have the aircraft move in a clockwise fashion. So that you see here, we've defined clockwise. We'll have the aircraft converge to that circle. And so if we let it keep going, then it'll continue to converge, and it'll get closer and closer and then start to follow that circle. One thing that we haven't played with yet is we can actually change this to counterclockwise, and we'll see that the aircraft will move around the same circle but in a different direction, right? So we have a counterclockwise motion. Okay, so let's go ahead and get started. So we'll first define the orbit or the circle itself, right? And the orbit, or this circle, is defined as all of the points. So again, this is using set notation. So we're going to have all of the points R in R3 such that we see that we're a function of C, rho, and lambda, right? So C is going to be our center of the circle. Lambda is going to tell us clockwise or counterclockwise. And rho is going to tell us the radius of the circle. Now, in terms of the set notation here, lambda actually doesn't matter. But this notation right here is we're going to take this phi, and this is just going to be an angle moving around in a circle. In a circle from 0 to 2 pi. So when this is a phi of equals 0, right? Phi equals pi halves, all the way down to when it gets back, it's also equal to 2 pi. So we move that angle phi. We just are basically taking this vector, a vector of radius rho, and we're just rotating it around the circle. Okay, so I'm going to actually get rid of that so that we can write some other stuff here. So this defines all of the points on the circle. And what we want, the goal, is to have the aircraft move to the circle and stay on the circle. Okay, so that's our main goal that we want to accomplish. All right. So let's look at a few things. If we look at this angle right here. So this is again defined from the north. This is going to be chi super naught is going to be the angle, the course angle that we would like to follow. This is the course angle to stay on the circle. Right? And it's always going to be tangent to the circle. Right here we have the position of our aircraft. So we have our position of our aircraft, and it's defined also in the northeast plane. We have the course angle of our aircraft, right? Which is just defined again from the north down to the direction that the aircraft is traveling. We're going to find this vector, this value d is the distance from C to our vector P. Right, so we have our position, or our distance from the vector. Rho, right here, that's the radius of the circle. Or we could call it also our desired distance. So we have that desired distance defined. We have our actual distance. And while in the set notation we just let phi go from 0 to 2 pi, we're going to kind of abuse notation a little bit. And we're going to let phi be the angle, right, from north to the vector d. Okay. Well, it's not the vector d, but to this vector that points to the aircraft. Okay, so there we have the definition of our orbit. Okay, again, we have our C is the center, rho is the desired radius. The one thing we didn't look at yet is lambda. If it's 1, we want it to go clockwise. If it's -1, we'd want it to go counterclockwise. So in this case, this guy was assuming lambda is equal to 1, right? And we can now look at defining our position of our aircraft with respect to this center. Okay, we're going to define things in a polar coordinate frame. So d we just define as just the magnitude of P minus C, right, in the northeast plane. So we're assuming we're not going to be controlling height independently. We can use our same height controller that we used previously, but we're just going to let d be the distance in the northeast plane from the center of the circle to the plane, or to the aircraft projected onto the plane. And so that's our distance. And again, this angle, phi, we can then define just by the inverse tangent of the east component of the air over the north component. So we can define this, our polar coordinates. So our polar coordinates, just again to highlight them, it's d and phi. So we have the polar coordinates, and one note on implementation. to do this, because we're dividing by something that could be 0, we want to always use our a tan 2, which is a 4-quadrant tangent, inverse tangent. We do PE minus CE and PN minus CN. Okay, that would avoid any singularities. So just like we just define the position of our aircraft in polar coordinates, let's define its motion also in polar coordinates, because that'll allow us because really all we want is we want D to go down to rho. So if we look at this goal, aircraft move to this and stay on the circle, we could write that as D converges to rho and stays at rho. Okay, so let's take a look at this. We're going to take our polar coordinate representation, and we want to find out what are the dynamics of our polar coordinates. So what are dynamics, or the time derivative of the polar of d and phi? So in other words, d dot, and this is actually not phi dot. We'll get to that in just a second. So if we have a new frame of reference where we let our eye be pointed towards from C to P, right? So it's going to be in the direction of C to P. And then if we look at J, it'd be in the orthogonal direction. Okay. So we're going to make this transform. We're just going to do, right, a rotation about the z-axis by phi. And we're taking, again, this is our Dubin's model, and we're going to just rotate that Dubin's model, the time derivative of our north and east position, and we're going to get the time derivative of d and the time derivative of something related to phi, and we'll look at this. Note that this is actually a translational velocity. So we're getting the translational velocities in this new frame. So that's not our rotational velocity. So, but doing the math, we just multiply that, our translational velocity, we're going to transform it into the new frame. And what we end up with is, after some trig, we have this nice relationship. So the top row is d dot, and this answers the question, why change frames? Because then it helps us find a d dot, which is really important. Now, that top row is d dot, but this guy, like I mentioned before, this is a translational velocity. And this is translational velocity orthogonal to the vector pointing from our C to P. So it's orthogonal to that vector. And we can note that our phi dot, well, if we just look at a relation, so this is translational velocity, the relationship between our translational and rotational velocities about a circle, if we're staying on a circle, and note that this translational velocity instantaneously is going to be along a circle that's, it's going to be parallel to the vector chi super naught. Right, so our rotational velocity omega is just going to be equal to our translational velocity all over some radius r. So if we look at ours, in our case, we have that V here. This is our d phi dot. R is going to be d, and omega is going to be phi dot. So where d phi is that vector there. So in this case, we have that phi dot is equal to, and we'll have our d phi dot divided by d, which is exactly this equation right here. So it's Vg, so this is our velocity tangential to the circle and divided by d. Okay, so we have d dot and phi dot, and as always, we have now, we have our autopilot model. So we have our autopilot model. Given a course angle command, how is it going to respond? Okay, so we know how we're moving. So right here, this is our motion in polar coordinates. Now it's dependent on our course angle, and it's dependent on phi, which is currently one of our states, right? So let's design a controller that'll send us to 0. Excellent. So again, let's kind of step back just a very second and review what we want to have happen if our distance is large, much larger or much smaller than rho. Sorry. So we have our rho, our desired radius. So if d is much greater than rho, well, let's actually do the d equal to rho first. So if d is equal to rho, we know what our desired heading is, right? So this is our, oops, I wanted to do blue. That's the desired course angle when d is equal to rho. So if we're on the circle, it's going to be equal to our chi super naught. Well, what is chi super naught? Chi super naught, if we look at the vector defined using phi, right? It's actually going to be orthogonal to that. So it's either going to be phi plus lambda times pi halves. Right? So if we take a look at that, it's phi plus lambda times pi halves, where lambda equal 1 is clockwise, lambda equals -1 is counterclockwise. So this guy right here, just think about what it is. If you think about it for just a second, we should see that that's the clockwise choice. So if we're right on the circle, that's how we want our desired orientation to be. Okay, but if we're really far away from the circle, so say we're out here, and again, this would be our angle phi, this would be our angle chi, all defined from north, right? So this is really our angle phi, this is our angle chi naught. Well, if we're really, really far away, we actually want to move towards the circle, towards the center. So really far away, this is going to be, again, another 90 degrees. So we want to move, this angle would be chi naught plus another pi halves. Do lambda times pi halves, right? Because if we were pointing in the other direction, we'd want to do another minus pi halves. Okay, so that will move us directly towards the center. So that's what's written here. So if in this case, our desired, this is slightly different from the line following. We're going to let chi sub d, this is going to be our desired course angle. well, where with a line we said that it was our deviation in the coarse angle. Okay, so slight abuse of notation there. But we have, again, we have our desired, if we're at the correct radius. And then if we're really far, we're going to do that, our chi super naught plus lambda pi halves. Okay, so in this case, we have our desired coarse angle is going to be our chi super naught, so if we're right on, plus lambda times, now we're going to do this tangent. So again, we have, this is again our sigmoid. And remember that this gives us a value of between minus pi halves and pi halves. So that's actually exactly the scaling we want. We don't have to, if you recall in the line, we rescaled it by 2 over pi so that we get between -1 and 1. In this case, it goes directly between negative pi halves and pi halves, which is just perfect. So that'll give us this plus pi halves term. So we want our, at infinity, would do, at our radius, our d being out to infinity, would do our initial coarse angle plus our desired orbital coarse angle plus lambda times pi halves, right? So this is pi halves at infinity, negative pi halves at negative infinity. Okay. Now, similar to before, we have this k, and this is k sub orbit. This is just a convergence factor, just like before for the line. And this is what we're going to call our relative radius. So our relative radius, that's defined as just the d minus rho all over rho. It basically is the, if we were to take it, look at it, it's the number of radiuses from the center C. Okay. From the edge of the circle. Right? Because if d is equal to rho, it's equal to 0. So we have the number of radii from that edge of that circle. So that's what we call the relative radius. Okay. So that's our desired orientation. Now let's figure out what should be our commanded orientation. And again, we're going to make the same assumption that we did before. In other words, again, we're not evaluating the low-level control, but we're evaluating, so we are evaluating the vector field. Okay, so if we are able to follow that vector field perfectly, will we get onto the orbit? And so what we do is we define our candidate Lyapunov function as d minus rho, so that way when we're at our desired radius, that's equal to 0. And so again, this is just going to be our partial derivative of w with respect to d times the time derivative of d dot, or of d, sorry. And similar to before, I think these relationships are really valuable to work through. So this will be on your, I should write that in red, right? So you'll have homework that helps you go through those relationships. So that way you're going to make sure you understand those relationships really nicely. Okay, so But up here we have condition number 1 for a candidate Lyapunov function. And here we have the fact that w dot is less than or equal to 0 is condition number 2 for our candidate Lyapunov function. Okay, so the key here is that d minus rho goes to 0 asymptotically. That means our vector field will, if we were a point on the vector field and we just followed that vector field, we would go to that orbit, which is really good. It doesn't say that our aircraft will go to that orbit. So a couple of things that we need to be careful of. We have our commanded course angle. What we need to do is we need to make sure we're wrapping. So here's our command. This is what we already developed. Okay. We're going to wrap our function phi minus our course angle to be between negative pi and pi. So we wrap our phi minus our course angle to be within negative pi and pi to ensure we turn in the correct direction. Otherwise, we could end up going in circles to get to the exact orientation we were already at. So then we compute the desired course angle and we send that in as a command. Okay, so first thing with our control is just to make sure that we're wrapping correctly. Now the second thing that we have to do is a feed forward term on our roll. So our convergence analysis did not talk about convergence of our actual control, right? Our actual control will not work perfectly, will not converge to the right radius. Because as we come in and as we come into the circle, what we're doing is if we have a command of just that guy, our error is going to be 0, and so our roll will then say that we should be at 0 roll. But in reality, if we're staying on the circle, we want to make sure we have a feed forward roll term. So we then give our feed forward roll just according to this equation, right? So again, it comes from the coordinated turn, and we're just taking the inverse tangent of this coordinated turn, and so that'll give our controller that feed forward in the roll that we want. Okay, so now we have the control. Let's move back to our state, and you can see that the whole time we've been lecturing, it's just been moving in one big long circle, right? Which is pretty cool. And you can see that in our x and our y directions, right? They look like the sinusoid. They look like a sinusoid because we're going around in a circle. And we're staying pretty close to our, this is our, we're staying right on our desired altitude, right? And just want to review again, this is pretty cool because we define our orbit. We give it a speed, so we could speed this guy up, right? So we have a desired speed. We defined with an origin. So if we move this out to x being at 100, right? We're gonna converge out to it, right? And we could even converge. Let's say this is negative 100, so move it again, right? So that's how we define our circles. We have this origin, and we have our radius. So now if we made it 300, not 3,000, 300, it'll go in. And we can send this command to our aircraft and have it go down, and we can converge to any arbitrary orbit. And the last thing we can do is we'll give it a really hard time, send it into clockwise rotation, and now it's going to have to turn all the way around to be able to go back to that desired orbit. Okay. If we want to give it a little bit of help, get to it faster. Right? So there we go. Now we're moving in a clockwise rotation. There you have it. So we've defined this vector field. We'll first define the orbit, then we define a vector field that'll take our desired course angle and have us converge to that value. And one thing I do want to show you is that we could have a height be something very different. So right now, if I were to look at this, we're right about that height, right? Now if we change this up, we just have our orbit up at a higher location, and we just use that same height command that we did for the following the straight line. There you have it. Now we have an orbit following control law.